It's really a pleasure to be here, and of course, a little bit intimidating. I'm intimidated because there are so many people that I know better than me, and well, I have a chance to talk about something that I think will be probably of interest to Chris, a new area for me, like density and... Okay, so let's get started. So we'll start from the setup that I will be working on, setup of reproducing kernel Hilbert spaces, just like closed subspace of, let's say, L2 of Rn, where point evaluations are continuous. Those Kx are reproducing kernels, right, where evaluations, so you have those kernels Kx, so that evaluation is continuous, right? So if you don't like this language, and okay, you can think of this as just frames, right? So reproducing kernel, if they form a frame, this is a language, this is a sampling set, right? A set is a sampling set for the reproducing Hilbert space. If and only if the reproducing kernels form a frame, right? So we have those bounds, okay, A and B as usual. Then you have notion of interpolation set, which I will not be talking too much. This is the reproducing kernel from a rich sequence. And of course, if you have simultaneously interpolation and sampling set, then you have Riesz basis, right? But essentially, we are in the language of frames. So now, what are the assumptions on the reproducing kernel? So this may be a little bit intimidating for those of you who haven't seen this important paper of Pierre Grosjenik, Jaime Klotz, and Romero, where they put some kind of natural assumptions, but at least one property I know that Chris worked on a lot, this homogeneous approximation properties should be well known. So what they assumed is that, well, we have diagonal conditions. So the norms of reproducing kernels are bounded from above and below by some constants. There's this weak localization property, which means that, well, if you take epsilon positive, you can always find radius r, so that when you take integral over ball, well, on Rn, but away from that ball, and then what you do, you integrate against your kernels. You fix x and you integrate against your kernels, you get a small integral, and then you take regardless what x is, right? So somehow, so this is some kind of localization of frames. Again, many of you probably have seen this. And this homogeneous approximation property, which I understand the least. I mean, well, I know that it's important, but it says that when you have a Bessel sequence for some countable set lambda and you have epsilon positive, then again you can find r, so that well, the sum here is over all set of indices away from that ball, right? And again, it's sort of similar to localization. You just look at the inner product against your Bessel system of reproducing kernel Kx. This has to be less than epsilon squared, right? So it has to be also small, so somehow regardless what x is. Okay, so I don't know. I really cannot really explain what this came from. I mean, we'll have to ask Chris to explain this, but maybe, yeah, but okay, I take it. I mean, this is the natural assumption. Okay, so now what they proved, and this is, I think, the importance of the paper, is that basically what the setup of this reproducing kernel Hilbert spaces is a setup, like probably right now, I would say the most general setting where you can still prove density results, right? So what are the density results? So suppose, again, you have our space with reproducing kernel satisfying this DC, which is this the DC, WL, and HAP. And if you forgot about this, let's just see. This is diagonal condition, weak localization, homogeneous approximation property. Then, if you have a frame, now you have a subset, right, indexed by capital lambda. If this is a frame, then certain density, and this is a lower Beurling density, has to be above the critical density. So here the critical density is 1 because we use some kind of dimension-free version of lower upper Beurling density. And this concept appeared in multiple talks before. What we are doing is that we take arbitrary balls, right? Balls run over the whole space, Rn. We count the number of points in our set and we divide by the measure, but the measure is not really measure of the ball. It's normalized by the norms of the kernels. And then, of course, for the lower density, we take infimum of these expressions, and then we take lim infas Argos infinity. So that's okay. So that's a necessary condition for existence of frame. For resequences or for interpolation points, I mean, the upper density has to be at most 1. And of course, when you have a Riesz basis, then both upper and lower are equal to 1. So I think this is probably I would say, the most general setting where you can do this. But, well, it's Rn, so I need to make a correction, and nobody corrects me because you're so kind. But I mean, it's not the most general Rn. Of course, you can talk about other spaces. So space Rn can be replaced by any metric measure space. So that's actually the second part of the story. Why this? So essentially you have a metric D and you have a Borel measure that satisfies, well, those 5 properties, but all those properties are satisfied by Rn, and they're very natural property. Like, okay, you want a space to have infinite measure like Rn, because otherwise somehow doesn't really make much sense to talk about those density results where you take R large. All balls have to have finite measure. Okay, so that's natural. Maybe this non-degeneracy condition is a little bit less clear, but okay, there is some radius R, so that when you look at all balls of radius R, they need to have measure that's bounded from below, right? They cannot be too small, right? So regardless what this ball is, I mean. And then there is this weak annual property, which means that when you take R going to infinity, and you look at like a boundary of your ball, I mean, so the difference between the ball of radius R plus 1 and R, look at the measure of that compared with the measure of the ball. I mean, this has to go to 0, right? So somehow annuals, and of course it goes uniformly. So we take supremum over all x, and then R goes to infinity. So of course, Euclidean balls also satisfy that. And the last property is like doubling at large scales. So not even at small scales, it's not needed, at large scales only. So we have a radius R0, and CD is this doubling constant, so that if you take R greater than R0, then the measure of ball of twice the radius is bounded by measure of the ball of radius R. And the result that I mentioned, that this is like the most general setting where the density results work. I mean, yeah, they work on those spaces, on those metric measure spaces. But I stand to be corrected. If you know more general results for Beurling density, please let me know. But that's okay. So this is that metric measure space setting. So now let's come to work of Radu Balan, Pete Kasaza, Chris Heil, and Zev Landau. And all of the people are in the audience, except of course, sadly, Pete. So this famous paper about in JFA. I think there are two papers in JFA. I didn't show the slide, the title page, but yeah, these are really nice papers about density over completeness and localization of frames. So what are on those papers, at least also in the papers that are of Radu and Zev, there is something called a frame measure function. So okay, so what is this? So suppose we have again a system of vectors in reproducing Kellner-Hilbert space satisfying this weak localization property, homogeneous approximation property, and we also assume that they are somehow bounded from below. And suppose we have a frame, right, for in our space, and then H lambda is canonical dual frame. So there is this relationship between density and this expression that only involves like frame elements and dual frame, canonical dual frame elements. So what you do is the following: you look at the inner products of your frame against canonical dual frame, this is always between 0 and 1, by the way. I mean, you take a sum over all lambdas that are in the ball of radius r, you divide by the number of points that are in lambda in that ball, and then you do infimum over all x and lim inf as radius goes to infinity. So you get this kind of expression, and this turns out to be equal to reciprocal of the upper Beurling density, and the same for this m plus function, which is reciprocal or lower Beurling density. And these are, those frame measure functions are, I mean, they somehow quantify redundancy of infinite frames. I mean, so if they if they are equal to 1, then you are almost like a basis, and if you are very close to 0, then you have huge redundancy. Okay, so that's so this result is essentially shown in that work of that I mentioned before of the Fier, Groschenik, Jaime, Klotz, Romero, but not really explicitly. But okay, so but you can also. I mean, this was well known for Gabor systems and for but it also holds in this general setting. Okay, so now yes, yes, this well, I mean, so yeah, this result I wouldn't say it's well, it is in our paper with Jordi van Veldhoven, but I mean, but it's not. It's essentially in that. Yeah, I mean, you are talking about this frame rate, right? So it is essentially in the work of Fier. I mean, this Fier, Groschenik, Klotz, Romero. That and of course again, I stand to be corrected. For Chris is here. I can probably ask him. I mean, so it's not for Gabor frames, and it's shown in your paper or in the paper of Radur.
It's related. So it's not exactly the same as the way that we stated it in our paper, but pretty close.
Yes, yes, because it's exactly. So, but I will try to get to like more familiar setting of Gabor frames, but okay, so that's maybe a little bit too much abstract stuff. But okay, so now, and maybe even this slide is even too abstract. Okay, but what we are trying to do, we'd like to construct frames near the critical density. So suppose we have a set of vectors that satisfies this frame measure density formula that was on the previous slide, right? And then what we would like to do, would like to be able to extract from this frame a frame that will have a lower density. Okay, so it's a bit dense slide, but okay, so but suppose that G lambda is a frame with some bounds A and B, right? Then what we are saying is the following. Suppose epsilon is positive, then I claim there is too many quantifiers and a bit, but it sort of looks like epsilon delta definition. But for every epsilon, you can find delta less than 1, so that eta is like, we'll see this in a second. Okay, so if your frame happens to have lower density above critical density, like 1 plus epsilon above critical density, right? So that's the frame that it's a little bit too much over complete. You would like to make it less complete. You can always find a subset lambda. That subset will have positive density. This condition with eta, this means that it has uniform. The subset has almost uniformly, that it's almost uniform density. So the upper density is always greater than lower density, but you can make it as small, this difference as small as possible, so that when you look at the upper density of the sequence lambda, but after remove lambda prime, this is less than that delta. Delta is less than 1 than the upper density of your original system. So somehow we can reduce the density of the original system by factor of delta, right? And then you still keep the same frame condition. Well, the upper bound will not change because, of course, that's a subsystem, but the lower bound is somehow controlled by epsilon, right?
So as long as you're above the critical density,
yes,
you can still remove a small set of positive density.
Exactly.
Come down a little.
Come a bit down, exactly. So, I mean, it's great that Chris asked this question or reformulates this, because Chris is an excellent expositor and I'm not. I try to focus always on research and, okay, I don't have time explaining that stuff. Okay, but exactly. So you have I will try to repeat what Chris said. I mean, you have a frame that's like one is critical density and you are really epsilon and you are above that critical density, like certain distance. You can always find a set that you remove of positive density so that the resulting system will be still a frame, but the upper density gets reduced by factor delta. So, and delta is less than 1. So maybe it's very close to 1, but it still gets reduced. And yes, but okay, so then the proof of this uses selector variant of the Weaver's KSR conjecture. So all these results are only possible thanks, well, probably in part to Pete, because he was the person who really infected at least me and probably first Darin. I mean, like trying to think about Cadison singular. Very easy to state problems in frame theory, but do not have answers. And we were really working on this really hard, let's say with Darin, and tried to solve it. Of course, we didn't, but then miracle happened and it was solved. I mean, like Cadison singular was solved, but then it was solved by computer scientists. And for me, the advantage of this is that they don't know that much of functional analysis. But okay, I know I know this. Okay, I can try to understand what are the ramifications of that. So this result was only possible using this Cadison singular. Again, it's a bit hard slide, but I'll try to first explain what is on the slide and then give you, I would say, like some explanation, intuitive explanation. Suppose, so it's essentially Weaver's formulation. Suppose we have Bessel sequence in a Hilbert space with Bessel bound 1. The norms of your system are small, like less than alpha, right? So then, okay, so now this is selector version. So now, suppose you have a disjoint collection of subsets of size at least R that partition your index set I. So somehow you group your Bessel sequence into those subsystems. So then what we are saying is there exists a selector. So there exists from each element of the partition JK, you can find one element so that you have a Bessel sequence, but with bound that's actually like almost optimal. I mean, the Bessel, you cannot go below alpha, so that's why, but the bigger the size R is, you can get closer to 1, right? You can get below 1. I mean, so now, okay, so Ulla is in the audience. And when Ulla came, I mean, I mean, as a child, what Denmark, I associate Denmark with. I mean, maybe, do you know what Denmark is famous for as a child? I mean, what? Lego, exactly, Lego. So I cannot explain this in terms of mathematically. Well, I mean, I cannot write what I wanted to say. I cannot write this in a paper, the intuition of this, but I'll try to explain you how I can view the Weaver's conjecture. By the way, Weaver conjecture is the one that actually formulation of Cadison singular that actually was solved. So it was the easiest. But what is the intuition for that? Okay, I can probably use this chalk. Okay, so when you have this system GI, right, you can think of this like a Lego blocks, and then from this Lego blocks, of course, you have frame operators. So something like that. So SFF, GI, right? So this is frame operator. And this frame operator is bounded by 1, right? Okay. So think of this, that you have like construction of Lego blocks. Of course, my picture is probably terrible. I mean, but like Lego blocks, right? And then essentially what what the Weaver KSR conjecture says is that you can partition this Lego. Okay, so what you can do? Oh, but by the way, I forgot one assumption. The GI squareds are less than alpha. So these are small Lego blocks. Like they are small, right? I mean, this is important. They are small. They are not big, right? Because so then what you do here, I mean, so the usual Weaver KSR, what it does, what Weaver said is that you can take this Lego structure, you can disassemble this Lego structure into R structures, which may not look, I mean, but each of them, I mean, they have size, which is 1 over, let's see, 1 over square root of R plus, right? So each of them, and this, you know, if R will be large, this will be less than 1. So you can, essentially what was important is that from this, and by the way, this Lego blocks, you can think each of the Lego block is like rank 1 operator corresponding to that, right? So essentially you can decompose this big structure into R structures, but each of them will have smaller size. So that's what we were, and that's what was proven. But now, what is the selector version? The selector version is slightly different picture. I mean, so selector version is, maybe you can think of this, there are like 2 players. So essentially what you do first, before somebody, like here you had a freedom how you disassemble this, right? But now, suppose somebody plays a game with you, right? And somebody puts like in groups of R. So these are those indices J1, J2. Well, it's everything is infinite, but okay. So and each of this like has at most like there at least are, let's say R equal to R. I mean, are Lego pieces in each of this, like in each of this group, right? Right. So you, essentially, you have disassembles this into those groups of R pieces. But now your task is to take from each of these groups to take one element, right? One element, and still produce a structure. So you have to structure this, right? I mean, so that again the size will be less than 1, right? And essentially, yes, that's what selector is. I mean, so there is a little bit, you have less freedom, but you only produce one structure. But even though it looks like a, but this is actually stronger. This is a, okay, maybe I spent too much time on this, but this is that's actually, this selector version actually implies the usual version of Haddison-Singer. That's, okay, so let's see, how much time do I have? Yes, because maybe I'm trying to hypnotize the audience. Because you are 15 minutes or?
5. No, sorry, no less.
Less, exactly. Exactly, but we started, I think, a bit late, right? I mean, okay. Okay, yes, okay, exactly. Yes, okay. Okay, so now using these things, I mean, we can prove it now? We can come back from childhood to adulthood, and we talk about mathematical things. So, okay, so if you, what we can prove is that, okay, again, when you have a frame in this setting reproducing Hilbert spaces, you can always find, well, you still have to assume that this frame measure density formula holds. Then for every epsilon, you can find a sampling set that will be as close to critical density, but here you have upper density. So upper density will be less than 1 plus epsilon, and you have a frame. So in addition, if you have Parseval frame, you have actually some control on the frame bounds that depend on the norms of the, like, because you assume here that these vectors are equal norm. And this is essentially shown by iteration, finite iteration of removing offset of positive buried density, but you need to have a starting point. So you need to have you start from a frame, and then that may have like large density, and then you will reduce up to 1 plus epsilon. So then this is another slide about frames near critical density, where, yes, again, you have reproducing Hilbert space and that satisfy these assumptions, well, you can always find a frame that will, well, but this is that setup of this normalized Berlin density so that you have a frame. So, okay, so let's probably get to stuff that's more familiar to us. So again, something like frames of exponentials. So what is the goal? So you would like to, given a set omega of RD, you would like to construct that has finite measure, would like to construct a frame for that, right? So this was shown only like by Vincent Olewski using the solution of Kadison-Singer problem, right? But then 2016, so then Freeman and Darin Spiegel showed that this is actually part of a bigger thing of discretization problem of continuous frames. Now, what things I wanted to say, I mean, the Kozma, Nitsan, Olewski finally found a set in 2023 that you cannot, regardless of what sampling set you take, you will never have a Riesz basis, right? So now, this is a more recent result from 2026 that you can find, well, sets with fine frames of exponential, and maybe Putin will talk about, I have to be careful because I cannot go over time and take time from Putin. He will talk about generalization of this to unconditional Chaldee frames, hopefully. Okay, so what we were able to prove in this work with Van Veldhoven is that regardless of what omega you take, you can always, and you take epsilon positive, you can always find a set of density, upper density, which is arbitrarily close to the critical density, which in this case is the measure of omega, so that you have a frame. And you actually have quite good control on the frame bounds. I mean, they depend on the measure and on epsilon. So that's what, okay, so what you can deduce. Now, Gabor frames. So Radu, Balan, Pitka, Saza, and Zev Landau showed that Gabor frames, existence of Gabor frames near critical density when the window is like well localized in this moduli space M1. So in what we can do, we can drop the non-localization property. So G is any function in L2, right? That's non-zero. Then for every epsilon positive, you can find a sequence of time frequency translates so that the upper density is less than 1 plus epsilon. So here probably that's probably a mistake here. I should be a bit careful about the balls. That should be R2D. And the time frequency shift of G form a frame, right? So that's what we can deduce again using those results that we have. And then Balian law theorem, of course, tells us that, yeah, we cannot expect to have Gabor frames at the critical density. So essentially, yeah, the best we can hope is to get arbitrarily close to critical density. Okay, so the last two slides are yeah, you can talk about like systems on groups with polynomial growth, which is, yeah, it doesn't have to be even abelian. So you have second countable locally compact group that has infinite measure. Polynomial growth means that you have some kind of relatively compact neighborhood of symmetrical relatively compact neighborhood of units, so that, well, when you take powers of that, you get the whole group, and then somehow those measures of those iterations grow at most polynomially, and then you can prove essentially the same result that when you have arbitrary unitary, maybe projective unitary representation of G, and you have vector which is admissible. So I mean, so this means that this is isometry. Then, oh, well, you have to assume something about a bit more about the window F. Yes. So you want the window G. So then again, you can construct frames which are arbitrarily close to critical density. And maybe the last slide, I think I will even spend less time on that. So this is some work of Groshenik and Klotz, generalization of polylinear spaces by second order differential equations. If this is Laplacian, then you get the actual polylinear space. But But essentially you have to assume something about the symbol that is positive definite, slowly oscillating. You consider this operator. This is identity, then it's essentially Laplacian. Then you, of course, you have to use functional calculus to define this unbounded operator, but that's okay. You look at that, that's a polylinear space, and Grotjnik plots show that this space lies in this umbrella of reproducing kernel Hilbert spaces, and they proved that if they form a frame, then so again they proved this density result that the frames have to have density greater than 1, and then what we were able to prove that you can get arbitrarily close to critical density. Okay, I think the lecturer is looking at me, and I think, am I on time? Okay, so let's give birthday to Chris.